Yeah. Foi eye control. Yes, sorry, I'm getting back. I was being shown something beautiful, how to do the recording instantly. Now, I was talking about the basis of chemical bonding. The basis of chemical bonding is to attain compound formation.
Excuse madam, your presentations are not seen.
Pardon?
The slides are not seen.
It is me who is now talking. Are you able to see me?
Okay, fine, please.
Because
Yes.
you'll be copying my slides that instead of listening to me. That is why I'm getting them off, okay? Eh,
Okay, fine, madam.
okay. Now, now, I was talking about the basis of chemical bonding. That these atoms cannot stay stably. They can't stay stably in their isolated state. For example, if you have sodium just sodium, or if you have chlorine as chlorine, it will not stay stable. So there must be a way of striking a balance. There are different ways in which this chemical bonding can be done. Either it could be sharing of electrons, joining by sharing of electrons. It could be bonding by losing of an electron, or it could be bonding by acceptance of an electron from another element. At the end of the day, the beauty of it is that you're going to form a compound which is stable. So now I'm getting back to the point where I left you. I was talking about carbon, the ability of carbon to form a bond within itself, and the ability of this carbon to share bonds with other elements such as hydrogen, such as nitrogen, such as oxygen, right? So, but how is carbon doing it? There are different ways in which chemical bonding can be achieved, which is the basis of this class actually. One, we have what we call covalent bonding. We are going to go through all of those types of chemical bonding of physiological importance. The first one we are going to talk about is covalent bonding. Carbon forms chemical bonds through sharing of electrons, and that is what we call covalent bonding. A covalent bond is a bond which is formed when elements that are involved in that bond formation do equally share electrons. When they do equally share electrons amongst themselves, then the nature of bond which is formed is what we call a what? A covalent bond. A covalent bond. This bond is formed between elements which are non-metal and non-metals. For example, an example of non-metal like carbon, another one like oxygen, another one like nitrogen. All those are non-metals. So if there's a bond which is formed between non-metal and non-metal, that bond is going to involve sharing of electrons amongst the elements that are involved in the bond formation. But I wanted to point out something, a point of physiological importance. That a covalent bond is a very stable bond. A covalent bond is a very stable bond. It is not easily disrupted under physiological conditions. You can take that note that a covalent bond is a very stable bond which is not easily disrupted under physiological conditions. And as such, a covalent bond explains structure formation. Our structures are made through covalent bond formation. That is a major point to reflect on. Your proteins, your DNA, your carbohydrates, your lipids, your vitamins, or anything that you call organic that is making up your human body is made as a result of covalent bond formation. That explains why your proteins, when you look at your hemoglobin is not going to be disintegrated unless otherwise the physiological conditions have been interfered with. Your DNA is going to remain intact. Your lipid structures shall be integral unless otherwise the physiological conditions are interfered with. Why? Because the covalent bond is a very stable bond under physiological conditions. Okay? Now, I want to point out something. I am getting back to the slide now. Getting back to the slide, I pointed out that very, very clearly. I wanted to mention something. Carbon, because of its ability to form bonds within itself, but also with other elements, carbon is able to form numerous organic compounds. In slide number 2, I show you the basis of carbon chemistry. Carbon is able to form diversity of organic compounds. When we used to learn what we call organic chemistry, we were taught about the organic compounds. So these organic compounds are defined by what we call functional groups. In slide number 2, I've pointed out some of the organic compounds, the possibilities of what carbon can form. Carbon, I pointed out that carbon can form carbon-carbon. Carbon can link up with oxygen, and you can form diversity of compounds, such as the alcohols, such as the aldehydes and ketones, such as the carboxylic acids. Carbon, point number 3, carbon can link up with hydrogen, forming what we call the hydrocarbons. Carbon can link up with nitrogen, forming what we call the what? The amines. So all those are diverse options that the element carbon can form when it links up with itself, but also with other elements. But the point I wanted to point out in this slide is that the behavior of these compounds differs. The chemistry of these compounds differs accordingly. But the chemistry of these compounds will influence the molecule where these compounds are found. So I'm going to take you back to do some revision of your organic chemistry. You were taught about these organic compounds, and they used to tell you about the behaviors of alcohols. What explains the chemistry of the alcohols? How do aldehydes behave? How do carboxylic acids behave? Or how do amines behave? The chemical behavior is largely contained in what we call a functional group. So in this slide, I'm showing you some of the functional groups which are highlighted in red. For example, alcohols have a functional group of OH. Carboxylic acids have a functional group of COOH. Aldehydes and ketones have a functional group of C, double bond O. But these functional groups influence the chemical behavior of these compounds. And as such, because of their chemistry, they will determine the behavior of the macromolecules where they are found. I'm getting away from there. I want now to talk from here. When we are doing structure, when we we are working on structure and the function. Each of these molecules, whether proteins, whether carbohydrates, whether DNA or RNA, has a certain way the structure looks like. The way it is outlined, the way it is folding. But what I want to point out here is that the way hemoglobin looks as is not by coincidence. The way your DNA is folding is not by coincidence. No. The folding, the structural makeup and the folding is determined by the chemistry of this compound. It is largely determined by the chemical constitution of the molecule. And what is explaining the behavior of this molecule is largely dependent in the nature of the elements that make up that compound. Take an example. If in the makeup of that molecule maybe is an aldehyde functionality, or maybe is an amine functionality, or maybe in the makeup of the molecule you have an alcohol functionality, there is a certain way alcohols behave which will not change, or there is a certain way in which amines behave. So dependent on the constitution of this molecule, the folding, as indicated, will be determined by the chemistry of the molecule of the compounds that are making up that macromolecule. That is why I'm saying that it is important you appreciate how do these chemical compounds behave. If we talk about alcohols, what is the chemistry of alcohols? What are the chemical properties? What are the chemical properties of aldehydes? How do amines behave? It is important. If you're to understand structure and functioning, it is important you appreciate the behavior of these organic compounds. I do have, let me see who was on. Ernest was on. You've just gone off. Can I take a question? Let me just first take a question before we proceed. Is there, before I continue, I want to take a question. Is there anybody who has a question? You people. Class?
Yeah, for me.
Okay, yes, I have Muhammad. Muhammad, can you say something?
I don't have no more to say.
Are you following?
Sorry?
Are you following?
Are you clear?
You're okay. Okay, that's fine. That is fine. Okay, now, I think that is a point which is driven home. We've talked about covalent bond formation, which is explaining structure formation. And I've urged you to appreciate the chemistry of the organic compounds because the chemistry of those compounds largely influences the structure makeup of our macromolecules. You can only understand how DNA is folding, you'll be able to understand how these proteins fold or how the carbohydrates look like by appreciating the chemistry of those organic compounds because the chemistry will influence the structure makeup of this compound. Okay? Now, I need to go through the third slide. Let us move on. Now, emphasizing the point I was talking about, in the makeup of an organic compound, we have what we call a functional group. A functional group is that group which explains the chemical behavior of a particular class of compounds. The functional group explains the chemical behavior of the compound. For example, when you look at compounds that we call collectively alcohols, why do alcohols, or what we call collectively alcohols, why do they behave in a similar way? The behavior is lying in the nature of the OH group. So all compounds that we collectively call alcohols do have a functional group of OH and explains the resemblance in the chemical properties of all those classes of compounds which we call alcohols. Take an example, carboxylic acids. All carboxylic acids have a functional group which is COOH. And there is a certain way they behave. Aldehydes have C double bond O. And there is a certain way they behave. So, but the point I wanted to point out here, or want to emphasize that the functional group and the nature of the ARA group. The ARA group is what we call the alkyl group. It is that group which attaches to the functional group. So the nature of the ARA groups and the functional groups will impart on the behavior of the biological molecules where they are found. So take an example. I gave you an example on slide number 3. Like, for example, if we have a carboxyl group, this carboxyl group which is ARA, the carboxyl group which is COO3, a carboxyl group always in solution. Whenever you put a carboxyl group in water, it ionizes. Ionizes meaning that it dissociates. It dissociates and releases a hydrogen ion in solution. Whenever you have a carboxyl group, it will dissociate in solution and releases a hydrogen ion. These hydrogen ions which are released in solution will cause the pH of that solution to go down, causing the medium to become acidic. So whenever you have a carboxyl group anywhere, whenever you have a carboxyl group, just know that in solution it is going to dissociate, releasing protons in solution and thereby making that medium to become acidic. So that means that if a macromolecule is containing many of these carboxyl groups, that macromolecule is going to largely adopt an acidic behavior. I'm going to get back to you. Let me first explain this. Another example I gave you here is that anamine group. Whenever you have anamine group, amine is this NH2. Amine groups in solution always accept protons from solution. And when you have R, the amine group R, NH2, added to a hydrogen ion, you form this ammonium ion. This ammonium ion is what is basic in nature. Because of a reaction between the amine and the hydrogen ion, the amine accepts the hydrogen ions from solution. Therefore, the concentration of the hydrogen ions in solution is going to go down, causing the pH of that medium to increase, making that medium to become what? Alkali. So meaning that in a molecule where you have several of those amine groups, in a molecule where you have several of those amine groups, there is a tendency of that macromolecule of adopting a basic behavior. So I've just pointed out those two. I've talked about the carboxyl. The nature of the carboxyl groups is that they will make the medium to become acidic. Amine groups make the medium to become what? Basic. But you will find other organic compounds which are nonpolar. For them, they can never dissociate in water. They can't mix in water. Whenever you put them in water, they self-associate out of water. And they are going to influence the behavior of the macromolecule where they are found. So that is why I pointed out that it is important for you to understand the chemistry of these organic compounds so that you can appreciate the structure and folding of our macromolecules. Forgetting not that functioning is largely determined by the structure of the compound. There is a reason why hemoglobin is the oxygen carrier. There is a reason why DNA is able to store genetic information. And the answer is lying in the structure of DNA. The ability of hemoglobin to carry oxygen is lying in the structure of the way of hemoglobin and how it is folding, which is enabling it to pick that oxygen. At the end of the day, if the structure is lost, if the chemistry is distorted, the structure is going to be interfered with, and so the function is going to be lost. And that is where the disease is going to come from. I hope I'm making a point on that. Is someone in class? Is there somebody in class?
Yes.
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 Are we following?
Yes, we are here.
Very nice. Someone is there.
Are you stable?
Yes, yes, madam,
We
you are going well.
yes, we are
You are going
stable.
well.
Yes, we are stable.
Okay, that is fine. That is fine.
You are going well.
Mm.
You are going well.
Okay, let us continue now. Yes, now I have talked about the covalent bond. I've talked about the covalent bond, and maybe a point of reminder is that a covalent bond, is formed when elements share electrons equally amongst themselves. And I pointed out that a covalent bond is a very stable bond. It is a very stable bond. It cannot easily be disrupted under physiological conditions. And therefore, it is important in structure formation. It is very important in structure formation. However, it is not the only bond. It is not the only chemical bond of physiological importance. It is not the only chemical bond of physiological importance. We have other types of chemical bonds of physiological importance. So I want to talk about the non-covalent forces. The non-covalent forces. The non-covalent forces determine the specific interactions which occur in a macromolecule. The non-covalent forces allow for interactions to occur within a macromolecule or between one macromolecule and another macromolecule. One thing we know of these non-covalent forces is that they are rather weak. These forces are weak, and so they are easily disrupted under physiological conditions. But I'll talk about the significance of that. The non-covalent forces are weak, and so they are easily disrupted under physiological conditions. Therefore, they are not useful in formation of structures. They are not useful in the formation of structures. Why? Because they are easily disrupted under physiological conditions. So among these, we have what we call an anionic bond, ionic bond. We have what we call the hydrogen bond. There is what we call van der Waal. We have van der Waal forces. We have what we call hydrophobic interactions. Of course, there are several other types of chemical bonds, but I wanted to point out those ones of physiological importance. So among the weak ones, the non-covalent forces, we have the ionic bond, we have the hydrogen bond, we have the van der Waal forces, we also have what we call hydrophobic interactions. And so I want to begin hinting on each of these bonds and where they are potentially applicable in our human systems. Beginning with the ionic bond, let us begin with the ionic bond. I talked about the basis of chemical bonding, where I mentioned that elements join with each other so that they can attain what? Stability. Otherwise, in their single states, in their isolated states, they cannot be stable. So the ionic bond, the nature of the ionic bond forms when one of the elements involved in bond formation completely loses its electrons, and those electrons are going to be accepted by another element. Let me get back to class properly. I can see Lily Jennifer with a smile. It is always on. And that energizes me when I see that she's smiling. that is motivational. So I'm talking about an ionic bond. Ionic bond forms when there is complete loss and acceptance of electrons. So one of the elements that is involved in bond formation must lose its electrons, and those electrons are accepted by another element. The result of the outcome of that nature of bonding is formation of a compound that we call an ionic compound. An ionic compound forms when one of the elements completely loses its electrons and those electrons are accepted by another element. The result is formation of a compound that we call an ionic compound. So this nature of bond forms between one of the elements which is a metal and another element which is what? A non-metal. One is a metal and another one is what? Is a non-metal. Take an example. A metal such as sodium can form a bond with a non-metal like what? Oxygen. The result is formation of a compound that you call what? Sodium oxide. Maybe you have a metal which is magnesium and a non-metal which is what? Chlorine. The result is formation of a compound that we call what? Magnesium chloride. So in this formation, one of the elements is what doing what? Losing its electrons, and the other is receiving those electrons. Metals lose electrons. Metals give away their electrons. Non-metals are always electron deficient, so they will accept electrons from the metal. I think there's a term I need to point out at this point in time. We have what we call electropositive. Elements that are electropositive have extra electrons to give out to another element. That is why they are called electropositive. So when we are writing them, when we are writing the chemical formula, we put a positive sign on them. For example, when you're writing sodium ion, you write sodium plus. When you're writing magnesium, you write magnesium 2 plus, like that. Why? That is indicating that this element bonds by loss of electrons. How many electrons? It is dependent on the elements. It is dependent on how many electrons that element is having in the outermost shell. But now I want to point out the physiological importance of this nature of the bond. An ionic bond is a very strong bond outside water. When not in water, it is a very stable bond. Possibly you've encountered rocks. Has anybody seen a rock? A rock. And how rocks are, how hard rocks are. Rocks are made from ionic compounds. The composition of rocks includes many ionic compounds. For example, calcium oxide, calcium phosphate, and several other ionic compounds. But a rock is able to stay because there is no water in it. A rock is able to stay because there is no water in it. But the moment you introduce water into an ionic compound, the bond is disintegrated. The moment you introduce water, the bond is disintegrated. So let me take back you to the slide where I'm pointing that out. So what I'm saying that these ionic bonds are strong in the absence of water. But the moment you introduce water, for example, we are looking at our cellular makeup. I believe we've already done the cell in physiology. And we know that the cellular makeup is water. The cytoplasm is water. So in an aqueous environment, like a cell, this bond, the ionic bond, is disrupted. The reason is that water ionizes. The chemistry of water itself ionizes. I want to see my class because I know what I'm talking about. Water ionizes, producing the hydrogen ions and the hydroxyl ions. If you have an ionic compound, for example, sodium chloride, and you introduce water into it, water ionizes, releasing the hydrogen and hydroxyl ions. So what is going to happen? Sodium chloride comprises the sodium cation and the chloride cation. So whenever you have a mixture of cations and anions, there is tendency of ions of opposite charge attracting each other. When water dissociates, it will give you hydrogen ions and hydroxyl ions. Sodium chloride has sodium ions and chloride ions. So there is tendency, if you have a medium of water with sodium chloride, the sodium ions are going to be attracted to the hydroxyl ions. Also, the hydrogen ions are going to be attracted to the what? To the chloride ions, causing the bond between sodium chloride to do what? To break. There's somebody I'm seeing who is sleeping. Hey! You're here dozing. Are you writing something? So I want to teach you the chemistry, but also understand the things that are happening in real life, things that you're living with. All of you have salt. Does anybody cook with salt at home? Do you have salt at home?
Yes.
Yeah.
Your common salt is sodium chloride. Your common salt
Sure.
is sodium chloride.
Sodium chloride is a common salt.
So what happens if you leave that tin of your salt open? What happens? What do you observe? I want an answer.
It dissolves.
It dissolves. That is exactly what I'm talking about. What is causing it to dissolve? It is attracting moisture. It is attracting moisture. When it attracts moisture, because water splits into hydrogen ions and hydroxyl ions, your sodium chloride has sodium ions and chloride ions. So the sodium ions are going to be attracted to the hydroxyl ions, which were present in water. And the chloride ions are going to be attracted to the hydrogen ions, which were present in water. So making that salt to be no more. It will make that salt to be no more. And that is what I'm telling you, that bond is very weak in the presence of what? Water. Therefore, when it comes to formation of structures, right now you're hearing me straining to talk to you. But I'll go back intact. By me using my mouth too much does not mean that it is going to remain apart. No. Oh, if you pricked me on the ear, doesn't mean that this ear, unless you've subjected a lot of tremor on me, but just me touching myself like this will not cause disruption of my skin. But why? Because I talked about the covalent bond. Covalent is in structural formation, but the ionic bond is a very weak bond. It cannot be used in the formation of a structure like a skin. Otherwise, it will dissolve. You cannot use ionic bond to form your protein. This skin is protein. Your hair is protein. Why? Ionic bond is very weak. The moment you introduce water, it breaks. However, does it mean that these weak interactions do not have a role in the body? They do have a role. I told you they enable specific interactions between the macromolecules and within the macromolecules. So when it comes to execution of function, that is when we use the weak interactions, such as an ionic bond. Are we getting the point? I'm saying in the formation of DNA, in the formation of protein, in the formation of lipid, in the formation of carbohydrate, we use covalent bond. That explains why your glycogen is stored in the cell and it is intact unless it is mobilized to be broken down. But when it comes to functionality, how is DNA copying information into RNA? Oh, how is hemoglobin able to interact with oxygen? That is when now you need a weak interaction such as an ionic bond. So during execution of function is when we use our weak interactions. Now, for those of you who are unable to see on the screen, you're in problems. Because if you're not happy, then I'm not continuing. I don't want to teach an anxious class. Are you following? You can just tell me that we are following. Hmm? Are you following? Mary, you're up there. Are you following?
We are following.
There's Jacinta. I don't know whether it is concentrating too much. I don't know. Elizabeth, who are you with in the room? Why are you putting on a mask? Eh? Elizabeth, who are you with in the room?
I'm in the hospital.
Oh, okay. I understand now. I understand. So now, if that is okay, I go back. I go back to the presentation. Yes, re-emphasizing our ionic bond. I said that the ionic bond is very weak in the presence of water, but also it is very weak in the presence of other salts for the same reason. If you put another salt in another salt, for example, if you have a medium containing sodium chloride, and then at the same time in the same medium, you have maybe magnesium phosphate, there is tendency of attraction, counter attraction of ions of opposite charge, causing the ionic bond to break. However, this ionic bond is important in several biological processes. For example, enzyme substrate binding, for example, antigen antibody binding, and the others. When it comes to execution of function, we need an ionic bond. So when we study, for example, enzymes, we will look at enzyme substrate binding. We will look at antigen antibody binding. Those interactions are enabled by weak forces such as an ionic bond. Okay? Next, I talk about what we call a hydrogen bond. There is another force which we call a hydrogen bond. What is a hydrogen bond? A hydrogen bond is a bond which is formed when hydrogen is shared between two electronegative atoms. When hydrogen is shared between two electronegative atoms. I'm back to you now. We do have, I talked about electropositive and electronegative. I talked about electropositive. Electropositive elements are those with excess electrons to give out. To another element, metals are electropositive. Non-metals are always electron deficient. They are always lacking an electron. And so they bond by acceptance of electrons from another element. So as such, we call them electronegative. What we call electronegative is because it is electron deficient. Therefore, it will require electrons from another element. And those elements that are electron deficient are always indicated with a minus sign. For example, you see us every day writing oxygen, and we write oxygen 2 minus. What does that mean? That it is bonding by acceptance of an electron, 2 electrons. You write chloride, Cl minus. What does that mean? It is bonding by acceptance of a what? A single electron. So now I'm getting back to the definition I want to talk about, which is the hydrogen bond. That the hydrogen bond forms when hydrogen is shared between 2 electronegative atoms. I've given the definition of an electronegative atom, and I want the class, I'm going to pick. Mary, turn on your microphone. Give me an example of an electronegative atom. Element. Example of electronegative element.
Oxygen.
Good. Another example. Jacinta, you've been here. Turn off. Jacinta, you've been here. Very attentive.
Is whether you said that.
Chlorine. Precisely, yes. Another example? Yes. Yes. There's Mary, you want to give another one? I love an interactive class. I cannot talk and talk as if I'm giving news on UBC. No. I want an interactive class so that I know that we are all enjoying what we are doing. So members have given an example of oxygen, an example of chlorine. All those are electronegative elements. So what is the nature of these electronegative elements? These electronegative elements are always electron deficient. They are lacking an electron, and they need a donor of an electron. But the scenario here that we have is that you're having 2 electronegative elements, and each of them wants a donor who is hydrogen. But hydrogen has 1 electron to give out. It has 1 electron to give out. Yet, there are 2 elements. There are 2 elements who are in need of that electron. You see that scenario? So what is going to happen? I hope I have something I can touch here to demonstrate what I'm trying to do what? To show to you. Can you see what I'm projecting here? Are you able to see it? Eh? Are you able to see this wire? You're not seeing the wire.
I'm not seeing. I'm not seeing.
Where did I go?
I'm not seeing.
Hey. Where am I? I'm looking for myself. Are you able to see it? Can we see it?
Yes.
Yes, we see it.
So now I want to show you something. In the middle here, this, you see this one? In the middle, hey, turn off your microphone. So I'm demonstrating something to you. I'm having a cable, but I want to use it as an illustration. I have this, what do you call this? I don't know what you call it. What do you call it in you people who are doing the electronics? This one.
Adapter.
It is what? I don't know what to call it, but this one over is the what? I don't know. But this one in the middle. Let us assume.
Adapter.
Hey, this is the adapter. Okay, right.
Adapter.
Okay.
Adapter.
Yes, I've heard. Now listen to my explanation. The adapter, assume the adapter to be having our electron. It is the one which is having the extra electron. Now we have this wire on this side. This wire on this side is lacking an electron. Therefore, it cannot transmit this power to the extreme end. But also, you have a cable which is joining from the left-hand side, which is also lacking what? An electron. But the scenario is that we have only one adapter in between, which is supposed to supply this cable, but also supply this other cable. Remember, we talked about the principle of chemical bonding. That chemical bonding enables attainment of stability. So what is going to happen? In order for this cable to become stable, it has to struggle to pull an electron from this adapter. But at the same time, this other one is also in lack of an electron. Therefore, it is also going to try to draw this single electron towards itself. At the end of that day, what you're going to observe is that it's going to be a pull from both sides. This one is pulling, but also this one is pulling. Oh, unfortunately, this one is weak, so it is coming out. But the scenario is that each of them is going to be pulling. At the end of that day, none of them is going to fully. What do I want to do? I want to bring back our presentation model. I want you people to come back on the screen. Okay? But I'm still finding it here. I want you people to come back so that I can see you properly as I draw my explanation. Where is it? Hey, but anyway, let me try to explain as I get back these settings done properly. What I wanted to explain to you is that you have one hydrogen atom. So there's one electron to give out. You have two electronegative atoms. Each of them is in shortage of an electron. Each of them is in shortage of an electron. But yet you have only a single electron to give out from one element. So here what is going to happen is that each of those electronegative elements is going to struggle to be pulling this electron. At the end of that day, none of them is going to win it. None of them is going to win it. So that is going to create a strain. It is going to cause a strain or a force of pulling. And that force of pulling is what we call a hydrogen bond. That force that is created as a result of straining or as a result of the two electronegative atoms struggling to adopt this electron. The force which is created as a result is what we call a hydrogen bond. I am looking for I don't know what I did, so that let me first work on these settings again, because I don't see my PowerPoint now again. Exit full screen. Okay. Present entire screen. Yes, I'm seeing it. Yes. Oh, first wait. There's something small I'm trying to bring back. No, technology is not easy. So now, are you able to see the slide again? It's gone off. I've seen it. I've seen it. So are we able to see the slide again? Now, getting back to what I was still talking about, right? I was talking about a hydrogen bond. That in the hydrogen bond, there must be two electronegative atoms. Each of these is deficient, so it is in need of an electron from an electropositive atom, such as hydrogen. However, because there is a single electron, none of the two elements is going to acquire that electron. At the end of the day, a force is going to be created, and that is what we call a hydrogen bond. Somebody mute your microphone, please. The result is what we call what? A hydrogen bond. Where do we find these hydrogen bonds? Hydrogen bonds are largely found in the formation of protein structures. Please mute your microphones. Please mute your microphones. Hydrogen bonds are found in structures of proteins. When we are looking at the way proteins fold, we'll talk about a hydrogen bond, but the amino acids in the protein structure are folded using what we call hydrogen bonds. Also, in the makeup of DNA and RNA, the bases that are making up DNA and RNA are supported in position using a hydrogen bond. So here I am showing you a cartoon of two bases that are making up the structure of DNA. What you observe in that structure, you see where I'm pointing the cursor? We are showing you on one side we have one base labeled G, it is guanine. On the opposite side we have another base which is labeled C, and that is cytosine. The joining of the two bases is enabled by a hydrogen bond which is denoted in red dots. So what you're seeing there is that in the linking up of these two bases, on the guanine side you have oxygen, on the cytosine side you have nitrogen, and in between there you have hydrogen. So you have electronegative nitrogen and electronegative oxygen. So the nature of the bond which is going to form in between there is what we call a hydrogen bond. I want to come back to my class again and hear from you. Although my setting has played me here, I cannot see all of us. I don't know what I did, what I clicked, though I would want to see everybody. But if you have anything that you want to question, you can raise up your hand and I pick you and you say something. Pause. We have about 5 minutes to end the meeting. If there's anything that we feel did not come out well, I'm going to encourage us to post something on the WhatsApp platform, see where you need help. I am going to share a recording. I'm sorry I was not able to do it during the week because I was so exhausted. So I could not do a lot of recordings. But now that we have had the class, I'm going to capture major issues from the presentation that we've had possibly complete all the slides on that lecture. You need to take some time during the week to listen to it. In case you have anything that you've not understood, you can always get back to me. So if we don't have anything to comment about, if we don't have anything to ask for now, I am going to say that our class for today has been successful. Okay. Let me just take record of attendance. Tell your colleagues that we do record attendance for every single session that we give for purposes of accountability to the institution and to your parents, spouses, or whoever is paying the school fees. Because once you pay, it means that you have to account for value for what? For money. If you pay and you're not attending these sessions, it is not good, not only for you, but also for the people who are facilitating your learning and the people who are responsible for meeting the dues to enable your learning. So I can see we've been having an average of 32 people. If we are supposed to be more than that, let us encourage others to always attend these meetings. Otherwise, thank you for coming. I can call this a successful session. So if you have nothing, you can leave the meeting. I will be the last person to get out of the meeting. Thank you very much. Please, feel free to leave the meeting. It has ended. Yes, we can leave the meeting.
Thank you, madam.
Thank you too. Thank you for attendance.
I like the way you present the last time. I like that.
Thank you very much. Thank you.
I'm feeling comfortable.
Okay, thank you. Any other concern or what you think or what you're suggesting? Yes, please.
Excuse me.
Yes, please.
How are you going to check our
Pardon?
how are how are you going to check?
The attendance? How am I going to take
Yes,
the attendance?
the attendance.
I already have it. I already have it stored.
Mm.
I already have it, don't worry.
Oh,
Hey.
oh,
These meetings are showing everything which is happening in the class. I have record of that already. Okay, thank you so
Hello.
much. Thank you so much.
Hello, Mohammed here.
Yes, please. I am listening in case there's anything. Others can leave the meeting. You can feel free to leave the meeting.
Sorry?
The class has ended. The class,
Network is very disturbance.
but the class has also ended. So you can leave the meeting, no problem. The class has ended. Otherwise, thank you for
Just
coming.
sorry, Peter. Sorry, Peter. We need your contact, please.
Okay, have a nice evening. Cause one okay, I just say okay. Oh, stop.